Okay, we are on poster pops now. I will bring up the list so you see who's up. All right, come on down if you see your name here. So in principle, you have 90 seconds. I think there's no double posters in this session. So, all right, who's up first? Okay, great. Let's see, you can just advance with this one.
Good morning. My name is Ayush. I'm a second year undergraduate student in computer science at IIT Gandhinagar. I'm working with Ashish Mahabal, Jacob Jensen, and the Rapid team as a summer research student at Caltech. My work focuses on machine learning based classification for rapid alerts. We use a staged multimodal model. In the first stage, rubber 80 acts as a real bogus model. Here, it combines science, reference, and difference image cutouts, along with PSF fit measurements, and survey and filter context. And candidates that are classified as real then move on to stage 2. In stage 2, in addition to the previous features, we also used the pre-alert light curve to classify these real sources currently as transient or variable. Working with Open Universe 2024 for HLTDS and the RIMTIM SIMS for GBTDS, we have evaluated the model on both high latitude and galactic bulge environments. The real bogus model improves performance substantially and improves the candidate alert stream. And the full multimodal model performs best for the downstream transient versus variable task. Thank you. You can see my poster number is 15.
Okay, thank you so much. All right. Next we have, yeah, thank you.
Hi, my name is Matt Lastovka. I'm a PhD student at the University of Maryland, and I'm interested in looking at exoplanet demographics in a galactic context. So more than 20 years of exoplanet demographics has shown us that the properties of planetary systems are strongly influenced by the properties of host stars. So stars of different masses, metallicities, even ages, have planetary systems that look different. And if we look at the galaxy hosts multiple different stellar populations, the thin and thick disk, the bulge, the halo, all of which have stars that have different distributions of ages, chemical compositions, and dynamical histories. And so we would expect that the planets in each of those populations should also look different. So I'm presenting some work that I'm doing to calculate occurrence rates, so basically how common are planets in each different population. So I have some preliminary results from a project using K2 that compares the occurrence rate in the thin and thick disk. And then I'm also looking ahead towards using Roman. So Roman is going to give us unprecedented access to planets in different galactic populations, but it's also going to present us with some unique challenges that we haven't had to face in previous surveys. And so I'm presenting a framework that uses galactic models and the statistical power of Roman to calculate occurrence across populations. So if you're interested in calculating exoplanet demographics with Roman and looking at exoplanets in a galactic context, come find me in my poster. It's number 17. Thank you.
Hi, I'm Maggie. I'm a PhD student here at Caltech, and my poster presents Supernova 2025 WNY, or WINNY, a gravitationally lensed superluminous supernova at redshift 2. So this work is part of a series of papers. My paper focuses on the supernova science, and our collaborators' papers focus on the lensing science. And together, we have the most comprehensive data set to date of any high redshift core collapse supernova, and the most detailed rest frame UV observations to date of any superluminous supernova. And this data set will be useful for a high redshift superluminous supernova science with Rubin and Roman. Winnie differs from canonical events in several ways. First, the rest frame far UV has a notable excess in its continuum in possible broad FUV emission features, which is very unusual at these phases, and little to no UV line blanketing. We also find evidence for carbon-2 H-alpha and possibly helium-1, potentially indicating partial stripping or an unusual ejecta-CSM interaction, since we find that the data are difficult to explain with any single standard powering mechanism. This work is in a paper, and it's waiting approval for journal submission, and we have a follow-up paper planned with James Webb NIRCam and NIRSpec observations from my approved program, with scheduled observations this fall and next spring. So if you're interested, please stop by poster 18. Thank you.
Hello everyone, I'm Yongming Liang. Now I'm an SAR fellow at the University of Tokyo. And we are very excited about the logical structure enabled by the Roman. And my poster in particularly focused on the cosmic noon. Protoclusters are known as the progenitor of the local massive clusters, and they are the very important site to regulate the galaxy evolution. However, how to quantify the evolving stage is kind of the missing piece. And here our idea is to utilize the gaseous reservoirs across the different scales and also phases to chase their evolving stage. And here we try to utilize the Lima alpha absorption and the extended emission, and also the hot gas enabled by the X-ray and SE signals, and also for the the condensed gas enabled by the hydrogen line ratios. And what Roman makes the difference is that we need to anchor such kind of reservoirs on the logical structure, like in the filaments, void, or cosmic nodes, and we need an unbiased galaxy mapping, and which exactly are enabled by the Roman grism. And especially the Redshift 2 is a big point because we can simultaneously map the O2, O3, and H-beta emission line for the star-forming galaxies, and also the DN 4000 and Balmer absorption for the passive galaxies. And also, different from the Hubble and James Webb, previously, we can only compare the density peak against the average field, but this time with Roman, you can see that one field of view can exactly map the entire protocluster and the feeding filaments, so that we can trace the the gradient, and which chasing the galaxy transformation from the average field to the filament and then to the cosmic nodes. So if that sounds interesting, please come to the poster 19 and maybe just grab me. Thank you very much.
Hi, my name is Yichao Lin from the George Washington University. I would like to talk about finding what Roman can do for finding classifying X-ray source. Now, there is a lot of very interesting X-ray source in the galactic plan that is in compact binaries, and we have detected hundreds of thousands of these X-ray source, and to know what they are, we need to classify them to find these very interesting compact objects. Now, to classify them usually by X-ray alone is not enough. That's why we have to look at the lower wavelength counterparts, and that's where Roman can come in with its incredible precision and depth. Now, of course, we have a lot of sources here. We cannot manually look at them one by one, so we developed a machine learning pipeline that helps with these kind of classifications. It had been used before for classifying Chandra source of tens of thousands across the whole sky. It had been using globular clusters. And if we look at the X-ray versus infrared flux plot here, you can see that this infrared J-band is quite a crucial part of separating different type of source. I also here have some example of that depth coming to play. For example, here is a X-ray source in the red circle, and if you look at it in 2-mass image, you can't really see a source there, but you go deeper and with better position, in VVV, you can see it, and of course with Roman, we can go even deeper. And with the machine learning side, you can see that on the feature important, which tell you what if a physical property is more important for the machine learning pipelines, infrared JBase is among the top 3. So with the Roman galactic plan survey, hopefully that will give us better source classification and better depth. If you're interested in more, come see me at poster 20. Thank you.
Hi, my name is Alexander Mosenkov, and I'm an assistant professor at Brigham Young University. And polar structures represent a unique type of peculiar galaxies in our universe, and they consist of 2 highly tilted components, the polar structure, typically polar ring, and the host galaxy. And these galaxies are pretty rare. Only up to 3% of local non-dwarf galaxies exhibit polar structures. And here you can see some examples of polar structure galaxies from our catalog. We just published the largest catalog of polar structure galaxies to date, consisting of 3,000 polar structure galaxies of different types, but all these galaxies are found at low redshifts, and so it's interesting to study whether these galaxies exist at intermediate and high redshifts. So that's why we used Euclid Q1 and JWST to identify more distant PSGs, and you can see some examples here, and we have identified a significant number of PSGs out to redshift 1 in Euclid Q1 and out to redshift 4 in the series survey. And this work demonstrates that these galaxies existed throughout much of the cosmic history, and of course with the Roman telescope we'll be able to explore their demographics and their formation and evolution. Thank you.
Okay, I think that's the last poster pop. Let's give a big round of applause for all the poster pops and all the speakers in this session. Thank you.